You already know this. You have known it your entire life, and you have never once questioned it. Ice is cold. You learned it before you learned to read, before you learned to write, before anyone ever sat you down and explained the world to you. You reached out, you touched it, and your body told you, cold. And your body was right, every single time. Undeniable, immediate, physical. A glass of water with ice in it sits on the table in front of you right now, and you already know, without thinking, without calculating, without any effort at all, that if you wrap your hand around that glass, you will feel cold. That's not a belief, that's experience. That's your entire life of evidence stacked up into one simple, obvious, irrefutable fact. Ice is cold. Except it isn't. And I don't mean that in a poetic way. I mean it in a precise, measurable, physical way that is going to make you question every single thing your body has ever told you about temperature.
Here's the number that breaks everything. Ice at 0 degrees Celsius sits exactly 273 degrees above absolute zero, the temperature at which molecular motion would theoretically stop completely. 273 degrees. That's not nothing. That is an enormous amount of thermal energy locked inside what you've been calling cold your whole life. So here's the question I need you to sit with. If cold is a real physical property of the ice cube, something the ice actually has, something it contains, something it radiates outward, then where exactly is it? Where does the cold live? Because I just told you the ice is vibrating with 273 degrees worth of molecular energy, so where is the cold hiding inside it? You can't answer that. Not yet. But by the time this video ends, you will, and you will never hold an ice cube the same way again. Alright, so let's do what any reasonable person would do. Let's figure out where the cold actually lives.
Your first instinct is probably this. Cold is just the absence of heat. Ice is cold because it doesn't have much heat. Simple, elegant, feels completely airtight. And honestly, this is a good answer. This is the kind of answer that sounds like physics. You've probably heard some version of this before, maybe in a high school class, maybe in a documentary, and it landed well because it has the shape of a scientific insight. So let's take it seriously. If cold is the absence of heat, then ice, being cold, must have very little molecular motion happening inside it. Molecules barely moving, nearly still, almost frozen in place. Except they're not. At 0 degrees Celsius, water molecules in ice are vibrating constantly. Not slowly, not reluctantly. They are locked in a crystal lattice, and they are oscillating back and forth with genuine, measurable kinetic energy. Energy that you can calculate, energy that you can detect with instruments, energy that is absolutely undeniably there.
And here's the number that makes this impossible to dismiss. To bring ice from 0 degrees Celsius down to absolute zero, the actual real absence of all thermal motion, you would need to remove 273 joules of energy per mole per degree all the way down. That's not a rounding error. That is an enormous reservoir of thermal energy sitting inside your ice cube right now. So cold is the absence of heat doesn't hold. The ice has heat, significant heat, measurable heat. The absence of heat explanation just died. Okay, fine, you adjust. New answer. And this one feels even more solid than the last one. Cold is relative. Ice feels cold because it's colder than your hand. You're not claiming ice has zero energy, you're just saying it has less energy than your skin, and that difference is what you feel is cold. That's it. That's the whole thing. This is actually closer to what thermodynamics says, and you know it. Temperature is relative. Hot and cold are comparisons, not absolutes.
The ice at 0 degrees Celsius is colder than your hand at 37 degrees Celsius, and your nervous system detects that difference. Done. Mystery solved. Except, here's where it completely falls apart. Think carefully about what you just said. The ice is colder than your hand, and you feel cold when you touch it. But what is actually moving between your hand and the ice when they make contact? Heat, thermal energy, kinetic energy transferring from faster-moving molecules to slower-moving ones. And which direction does that transfer go? From your hand into the ice, not from the ice into your hand. There is no cold flowing out of the ice and into your fingers. Heat flows from high energy to low energy, always. That is one of the most ironclad laws in all of physics, the second law of thermodynamics. Energy moves from where there's more of it to where there's less of it, and it never ever goes the other direction on its own.
So when you touch that ice cube, here is what is physically happening. Your hand is the source. Your hand is the high-energy object. And the ice is pulling thermal energy away from you, not pushing cold into you. There is no cold particle leaving the ice and entering your skin. There is no cold wave, no cold field, no cold radiation. Cold has no mechanism for transfer, because cold is not a thing that transfers. What transfers is heat, out of you, into the ice. You are not receiving cold, you are losing heat every single time. And that means the ice isn't doing anything to you. You are doing something to the ice. So now you have no answer left. Cold is the absence of heat? Gone. Cold is relative. It's just lower temperature. Gone. Both of your best explanations have been dismantled by the same physics. The ice cube is sitting there. You can see it. You can touch it. And the sensation it produces is completely undeniably real. But cold, as a property the ice possesses, as something it contains, as something it sends into the world, does not exist. So what is the ice? Here it is. One sentence. No qualifications, no softening. Ice is not cold. Ice is a heat absorber, and every sensation of cold you have ever felt in your entire life was your own thermal energy leaving your body. That's it. That's the whole thing. Let that land for a second. The ice cube in your drink right now is not radiating coldness outward into the world. It is not projecting a cold field. It is not sending anything into your fingers when you touch it. What it is doing, what it has always been doing, is pulling thermal energy away from everything around it, away from the liquid in your glass, away from the air above it, away from your fingertips the moment you make contact. The ice is a drain, not a source. And you, your hand, your skin, your body running at a steady 37 degrees Celsius, you are the source. You have always been the source.
Now, here's the mechanism, and it's simpler than you think. Heat flows, always, relentlessly, from regions of higher thermal energy to regions of lower thermal energy, and it does this through a process called thermal conduction, the direct transfer of kinetic energy between molecules in physical contact. Your hand has fast-moving molecules. The ice has slower-moving molecules. The moment they touch, your fast molecules collide with the slower ones and hand off their energy, like a fast billiard ball slamming into a stationary one. The energy leaves your hand. It enters the ice. Your nerve endings detect the drop in your skin's thermal energy and send one signal to your brain: cold. But that signal is not reporting the arrival of something. It is reporting the departure of something. Your brain just never told you that. Let's go deeper. Because what's actually happening inside that ice cube, at the level where physics gets uncomfortably real, is stranger and more beautiful than the explanation you just heard. Water molecules in ice are not floating freely the way they do in liquid water. They are locked, held in place by hydrogen bonds, electromagnetic attractions between the slightly positive hydrogen atoms of one molecule and the slightly negative oxygen atom of another, forming a rigid, repeating crystal lattice, a geometric prison made of electromagnetic force. And inside that prison, every single molecule is still moving, vibrating in place, oscillating back and forth within its fixed position in the lattice, constrained but never still. That vibration is the thermal energy of the ice. That vibration is what your 273 degrees above absolute zero number actually looks like at the molecular scale. Now, your hand makes contact. Your skin cells are mostly water, and the molecules in your skin are moving significantly faster than the molecules in the ice. When the two surfaces meet, your faster molecules begin colliding with the slower lattice molecules at the boundary. Each collision transfers a fraction of kinetic energy from your molecule to theirs. One collision, then a billion more, happening simultaneously across every square millimeter of contact surface in a fraction of a second. Your molecules slow down, the ice molecules speed up slightly, and if enough energy transfers, they eventually break free of the lattice entirely. That's melting. That's the ice cube in your drink shrinking while your hand gets colder. You are literally dismantling the crystal structure of ice with your own body heat. Now here's where it gets even more precise, and this is the part that explains something you've noticed your whole life without ever being able to explain. Metal feels colder than wood. You know this.
A metal doorknob in winter feels brutally cold. A wooden door at the exact same temperature barely registers. Same temperature, completely different sensation. Why? Because the sensation of cold is not about temperature. It is about the rate at which heat leaves your hand. Metal has high thermal conductivity, around 50 watts per meter per Kelvin for steel. Wood has 2 watts per meter per Kelvin. Metal pulls heat from your hand approximately 250 times faster than wood does. 250 times faster. Same temperature, same air, same hand. But the metal drains you so quickly that your thermoreceptors, the nerve endings in your skin specifically designed to detect changes in thermal energy, fire intensely and urgently. The wood drains you slowly enough that you barely notice. The coldness was never in the metal. It was never in the wood. It was always in the speed of your loss. And this is where you have to stop and recognize what's actually governing all of this. Every single transfer of thermal energy, from your hand to the ice, from the metal to your hand, from the sun to the earth, is mediated by electromagnetic interactions between molecules. The hydrogen bonds holding the ice lattice together, the electron clouds repelling each other when molecules collide, the oscillating electric dipoles that pass vibrational energy from one molecule to the next, all of it electromagnetic. When you feel cold, you are feeling electromagnetism redistributing kinetic energy at the atomic scale across the surface of your skin. The ice cube in your hand is not a simple object. It is a node in an electromagnetic system that connects your nervous system to the fundamental forces of the universe. Every time you've ever felt cold, you've been feeling electromagnetism. You just didn't know it. Right now, as you watch this, your body is radiating heat. Not metaphorically, physically, in every direction. Your skin is continuously emitting infrared radiation, losing roughly 80 watts of thermal energy into the air around you at rest. The same wattage as an incandescent light bulb, just invisible, just constant, just you, broadcasting energy into the world every second of your life. Every surface you touch receives some of that energy, or pulls more of it away from you. The chair you're sitting on, the phone in your hand, the air against your face. You are not a passive observer of temperature. You are a thermal event, continuously negotiating energy with everything around you. And here's the thing that should genuinely stop you for a moment. You have never, not once in your entire life, actually felt cold. Every time you reached into a freezer, every time you pressed an ice pack against your skin, every time you stepped outside in winter and felt that sharp, immediate bite of the air, what you felt was not cold arriving. What you felt was you leaving, heat leaving your fingertips. Thermal energy departing your skin cells. Your body's carefully maintained 37 degrees Celsius bleeding outward into a world that was simply more willing to absorb it than you were to give it up. Every sensation of cold you have ever had was a sensation of loss. Your body just never framed it that way. Feynman once said, and this is worth sitting with, that the most remarkable thing about science is not that it makes the world seem smaller and more mechanical, but that it reveals the world to be so much stranger and richer than anything we could have invented. He understood that when you look at something ordinary, really look at it, what you find underneath is never disappointing. It is always more. The ice cube you've been holding in your mind this entire video, it's still there. But it isn't what it was 10 minutes ago. It's not a cold object anymore. It's a mirror. It's showing you that you are a thermal system, that your body is constantly, actively, invisibly interacting with the physical world at the molecular level, negotiating energy with every object you touch, every surface you press against, every glass you wrap your fingers around.
You are not separate from the physics. You are the physics. The ice doesn't have cold, it has absence. And your body, trying desperately to fill that absence, reaches out with everything it has. That's what you've been calling cold your whole life, your own generosity. If this changed how you see something as simple as an ice cube, imagine what else you've been misreading. That's what physics does. It doesn't just answer questions. It shows you that the questions you were asking were never quite right to begin with.